Hello there, geometry class. Hey, as we are moving through our lessons and learning all sorts of things about shape and area and whatnot, I have an interesting problem to present to you. And that problem has to do with probability. Now, many of you have already studied probability, and so you're quite familiar with it, or maybe probability is something new to you. The idea of probability is it's the likelihood of something happening, right? And it just is usually written as a percentage or as a fraction. But probability is a number between 0 and 1. Between 0 and 1, with the idea of 0 being it is impossible, it can't happen. And 1 being certain. Right, and so again, these are usually written as a fraction or as a decimal, or again, if it's a guaranteed thing, it's 100%. It's a sure thing, or the whole number 1. Now, when you apply it to geometry, and there are a lot of real examples of this because we live in a physical world, the question changes a little bit. And what I'm talking about is, in the real world, how many points can you fit on my phone? Right? How many numbers are there on a line? How many points are in an acre of land? Well, actually, all those answers are infinite. So there's an infinite number of points on a line. There's an infinite number of points in a two-dimensional space or a three-dimensional space. So when we look at geometric probability, we're looking at the percent of the area that satisfies what we're looking for out of the total area possible. And when I say that, what I mean the total area possible or the length possible, that is the denominator. Basically, that is our real space. And we're saying, what's the probability that we land in a certain portion of that real space? So you may want to pause this table or just look at it with me, because when we talk about the length, the sample space on a line or in a length means all the points from A to D. The event, the probability of the event occurring that we're looking for, would be all the points between B and C, including B and C. So as a probability, you would say, oh, the length from B to C out of the entire length from A to D, right? That would give you the probability of an event happening. Here on a circle, what you're saying is, well, this portion of the circle, right, which would be the measure of that angle out of 360 degrees. And when you get into area, right, you're saying, well, this triangle, what's the probability of, given that we land in this rectangle, what's the probability that we land in this blue triangle? Well, it would be the area of the triangle over the area of the rectangle. Now, the question here is, if P is the likelihood that an event will occur, what is the likelihood that it won't? Well, that's just 1 minus. Remember that the probability of something happening plus the probability of it not happening adds up to be 1. Okay, so let's apply this in the real world. Let me get my face out of the way. What are the odds, I should say, what is the probability that a random point falls on BD? So I'm saying, oh, what's the probability that a random point falls between here and here? Okay. Well, the entirety of it is 4 plus 3 plus 5. And I'm really only concerned with the 3 plus 5 portion of it. So that would be 8 out of 12, which is really 2/3, which is roughly 67%. Sound reasonable? So this is how you apply probability in one dimension, because you're talking about a line. Time is one dimension. Height is one dimension. Any length is one dimension. Now let's try a little more complicated problem. Use the information below. What is the probability that the light will not be red when you arrive? All right, well, when we look at this is a traffic light signal, so this is actually a time problem. And remember, time is one dimension. We can actually plot it like it was just length. All right, so the light is green for 25 seconds, turns yellow for 5, and then everybody speeds up and goes through it. No, everybody slows down, comes to a stop because they're not going to make it and they don't want to cause a safety issue. So anyway, the question here, what is the probability that the light will not be red? Well, there's two ways to do it. Probability of not red means 1 minus the probability of red. Okay, well, the probability of red is 30 out of, let's see, 25, 5, and 30 is 60. So it'd be 1 minus that, and that's 1/2 or 50%. Of course, the other way to do it would be to say, oh, what's the probability of not red? That would be the probability of green, 25, plus yellow, 5. That's also 30 out of an entire 60-second cycle. And again, that cycle then repeats after it. I have 2 more examples for you, and you're through, and then you just get to apply the heck out of it. Of course, we need to talk about angles. Whoa! Hi! Look at that. When you deal with angles, again, in a circle, you've got 360 degrees all the way around. So what if I said, what is the probability it lands in a purplish region? All right, and I better use a purple marker, otherwise you guys are going to throw a fit. It didn't work. Probability of purple-ish. Well, let's make that purple-ish. Well, which colors are purplish? Now, this 75, that is definitely purplish. And this one, it depends on the screen. On the whiteboard, it looks more blue. On my computer, it looks definitely more purple. So what we're going to say is purplish would be 75 degrees plus 60 degrees out of a total of 360. Right? And again, you can write this as a simplified fraction. You can write it as a decimal, or you can write it as a percentage. I'm going to do mine on my calculator right now. So it's 135 out of 360. Right? And that's 37.5%. So far, so good? Good. The last thing we need to talk about is how we put everything together. And so here it says, find the probability that a point chosen randomly inside the rectangle, okay, so meaning given I'm inside the rectangle somewhere, that's my sample space, that it is not inside the triangle, the circle, or trapezoid, round to the nearest hundredth. Okay, this problem's a little more complicated, bear with me, but let's look at the big picture. The probability of it being in that rectangle in the first place, right, is 100%. So that's my denominator. So the big rectangle looks like this. 45 times 20. Okay, so really when I do that, 45 times 20 is 900, and I'm in meters squared. Now, what I need to do is figure out the areas of really just this triangle and this trapezoid and add them together and subtract them from the rectangle. Because again, I'm saying this sort of shaded region around those figures. So let's do that. So again, I'm going to say rectangle minus triangle plus trapezoid. Okay, and again, I already figured out the area of the rectangle is 900 minus. Now, the area of the triangle. Oh, I'm going to have to think about that one for a second. Let's do the trapezoid. The trapezoid's definitely easier. Right, because you're saying the trapezoid, this one here, would be 1/2 the height times the 2 bases added together, 12 plus 3. So I've got 15 times 5, 75. So I got the 75 meters squared. Now what I need to do is figure out this one right here. Now if you recall, this is a regular, let me go back one step. You may notice here that this is I didn't want to lose everything, that this triangle is a regular triangle. And how do I know that? Well, see this point here? it's 6 meters in a radius to all 3 sides, which means if I want to elaborate this a little more, really I've got something like this. And again, that's why you're saying, oh, wait a minute. Yep, that is definitely a regular triangle. Now, if you recall, when we did these special polygons, there was a shortcut here. And the shortcut is, okay, wait a minute, that means all 3 of these sides are congruent. So these are 60 degrees. And that means I've got triangles that look like this. And this is 60, and this is 6. So that's a... Wait a minute. No. So no, I split it in half. I'm sorry, I split it in half. So I go like that. And then this becomes a 30. There's my 60. This is 6. And what you should be able to then pick up and say, well, wait a minute. If this height is all 6, then this length is not twice that, but 6 times the square root of 3. And I know this problem has now just gotten more complicated, but don't fret. You can handle it. All right, so the big deal is then, when I have another one like this, like that, this is also 6 square roots of 3. So the area of this big triangle, right, the area of a regular polygon is equal to 1/2 the apothem times the perimeter. And what does that mean? Yeah, I know, this problem gets complicated. Area equals 1/2. The apothem was 6. The perimeter was 12 square roots of 3 times 3. Holy cow. You know what? It's really not that bad. It's just a number. What's half of 6 is 3. 3 times 3 is 9. And then I can do clear 9 times 12 square roots of 3. And that's 187.06. I'm going to add 75 square meters to it. I get 262. So I get 900 minus 262.06 over 900. Right, so I do 900 minus second answer, 637 divided by 900, and I get 0.7088. And if it says round to the nearest hundredth, that means this is actually 0.71, which is another way of saying 71% chance that given you land inside this rectangle, you do not land within the triangle or that trapezoid. And you may think, well, I don't know if that seems right. It seems like there's a, I don't know. But actually, if you did your math right and you calculated your areas correctly, this triangle and this trapezoid don't take up that much space. In fact, they only take up 29% of the total space. Right, so there's a lot of area surrounding it. I know that's a big problem. I know that's a lot of work, but actually we're at the end of the year. This is where we tie everything together. I hope that was helpful. Hope you learned a bunch. Miss Vanessa and your classmates are here to help you, and good luck. I'll see you on another time.